All right, 2015, number 3. Johanna jogs along a straight path. For time from 0 to 40, her velocity is given by the differentiable function v. Selected values are given in the table above. Use the data in the table to estimate the value of v prime as 16. So we're given the table, and time goes from 0 and then 12 and 20. We don't have, 16, but the rate of change at 16, that's going to be the average rate of change, right? 16 falls within that interval. So we're going to do v prime of 16 is equal to v of 20 minus v of 12 over 20 minus 12. So this is 240 minus 200 over 8, 5 meters per minute squared. Okay? Because what do you have? Your numerator, right, is in meters per minute. Your denominator is in minutes, so it's meters per minute per minute. Okay? All right, part B. Using correct units, explain the meaning of the definite integral 0 to 40 absolute value of v of t. So what is that in the context of this problem? It's the total distance. So 0 to 40 v of t dt is the total distance. Now it says using correct units. So it's the total distance in meters traveled by Johanna, right? Or traveled, whatever. From 0 to 40 minutes. Okay? So it's the total distance in that interval. And then it says, approximate the value using a Wright-Riemann sum with the 4 subintervals indicated in the table. Okay, so this is going to be, all right, so a Wright-Riemann sum. So the first interval, t is 12, so it's 12 times. The Wright-Riemann sum means we take the second endpoint, so 200, right? Plus, the next interval has a length of 8 times 240, plus 4, okay? And here's the deal. It's got to be positive 220 because it's the absolute value of all of them, right? Plus, the next interval has a length of 16 times 150. Yeah, so you're supposed to do that without a calculator, yeah. Well, so here we get 2400. And then, this one, you just have to bite the bullet into it, right? 8 times 24 is 192, so 1920 plus 880 plus 16 times 150. 4 times 150 is what? 600 times another 4, 2400, right?
24.
So 6 times, I'm sorry.
16?
Okay, so look, 4 times 150 is 600. But this is 16 times, so times another 4.
Yeah.
Okay?
I did 15 times 15 equals 225.
That works too. That works too. Okay. So altogether, that's 7,600 meters. Okay. All right. Part C. Now, that was Johanna. Now, Bob makes a cameo. Bob is riding his bicycle along the same path. For t from 0 to 10, Bob's velocity is modeled by this function. where t is measured in minutes and b of t in meters per minute. Find Bob's acceleration at t equals 5. Well, acceleration is the derivative of velocity, right? So we say for part C, you have to say b prime of t is equal to 3t squared minus 12t, right? Just take a derivative. And now we want b prime of 5. 3 times 25 minus 60, 15. What are the units?
Meters per minute. Meters per minute.
Squared. It's the acceleration. Meters per minute per minute. Okay, D. Based on the model B from part C, find Bob's average velocity during the interval. So this is the velocity. You want the average velocity. Average value is 1 over b minus a, integral a to b, blah, blah, blah. All right? So average velocity equals 1 over 10 minus 0, 0 to 10, the function t cubed minus 6t squared plus 300 dt. So that's something, that's a formula you need to memorize. Given a function, the average value is 1 over b minus a, integral a to b. All right? So here, this is going to be 1 over 10. And let's take the integral here. T to the 4 over 4 minus 2t cubed plus 300t from 0 to 10. And thankfully, it's all multiples of 10, right? So 1 over 10. Here we have 10,000 over 4 minus 2,000 over nothing, just 2,000 plus 3,000. And then, of course, it's all divided by 10, right? Okay, so 1,000 over 4, that's 250 minus 200 plus 300. You see how nicely it works out. So it's 350. What are the units?
Meters per minute squared. Because it's velocity.
Yeah, exactly.
It's just meters per minute.
Because if our
Oh, velocity. Oh my.
Okay, so look at what happened here. This here, you've got like blah, 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 dt, and then you're dividing by time, right? So this unit of time and this unit of time cancel each other out. So you're just left with this, which is a unit of velocity, meters per minute. Okay? Fabulous. Okay. Let's go to number 4. Differential equation. dy dx equals 2x minus y on the axes provided. Sketch a slope field. Okay, let's do this. Let's start with the bottom ones. Okay, well, actually, let me do this. So this, right, along the y-axis, x is 0, right? So x is 0 there. That means the slope is just negative of the y. If y is 2 here, negative of the y, this is negative 2. This, I'm sorry. Yeah, I'm right. This is negative 1, and then this is positive 1. Okay? So find patterns like that. It makes your life a lot easier. Now here, all along here, x is 1, right? So when you plug in the first, so it's going to be 2 minus whatever your y is, right? So 2 minus 2, that's 0. 2 minus 1, that's 1, right? And that was negative 1. So make sure like they're symmetric so you can show the difference. And then here, it's 2 minus minus 1, so 3. And here we just have to do like a super steep slope. You just have to show a difference, right? Do you see how my, slope of 2 looks different from my slope of 1 and here? right?
If you're unsure whether or not your slope will be clear,
Just write m equals,
yeah, can you label it for clarification?
yep,
And they'll accept that?
They're usually really good at that. I mean, they can pick them out pretty well. Find d squared y dx squared in terms of x and y, and then determine the concavity, blah, blah, blah. We'll take care of that later. So let's find d squared y dx squared. D squared y dx squared, so this is part B. This is d dx of dy dx, which is 2x minus y. Okay? So this is d dx of 2x is just 2, minus d dx of y is dy dx. And we know dy dx, 2 minus 2x plus y. Okay? Now, the second portion of this part says, determine the concavity of all solution curves for the differential equation in quadrant 2. So we want the concavity in quadrant 2. Remember, concavity is determined by the sign of the second derivative. I have the second derivative here. I just need to know in quadrant 2, is that positive or negative? So in quadrant 2, right, x is negative and y is positive, correct? So yeah, so 2 minus 2x plus y. If x is negative, then it's 2 plus something. And then y is also positive, so it's just all plus. Okay, yeah, so therefore, all solution curves are concave up. Right. Okay, C. Okay. Let y equals f of x be a particular solution to the differential equation with initial condition f of 2 equals 3. Okay. Does f have a relative minimum, a maximum, or neither at x equals 2? Okay, so at x equals 2, right, in order for this to have a relative minimum or maximum, there is, because this is not a closed interval, there is only one way for that to happen, and that's if there is a horizontal tangent, right? That means if f prime is 0. Okay, so let's see. For part, what part is this? C. F prime, meaning dy dx, evaluated at 2, 3, is 2 times 2 minus 3, which is 1. Since at that point the slope is 1, right? That means it looks like, it's just, like increasing at that point. So there is no minimum or maximum there, right? So we say, what is the question? Does f have a relative minimum, maximum, or neither? So, since dy dx is not 0 at 2, 3, there is neither a min or max. Okay? Next, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. All right. If y equals some function is a solution of this, that means it must satisfy this for dy dx, right? Whatever solution I get, y equals blah, 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 it has to satisfy dy dx equal to 2x minus y, right? So if this is going to be a solution of that, then dy dx, right? What is dy dx of this? It's d dx of mx plus b. The derivative of mx is m. The derivative of b is 0. So The derivative of this is m, right? But in order for this to be a solution of that differential equation, the derivative of that must equal this. Okay? So we say dy dx is 2x minus y. This has to equal 2x minus y. Okay? Now, what do we need to solve for? M and b. Well, look at this equation. I have m, I have x, I have y, too many things. I need to get rid of one of them, right? So I say m equals 2x minus, what is y? mx plus b.
Whoa. That's confusing.
I know. This is a confusing
I
one.
didn't expect you to
Yep.
like.
So that's the reasoning. So those are the steps. All right. It has to be a solution of that. That means if it's a solution, when you take a derivative, you must get 2x minus y. So when you take a derivative, you must get 2x minus y, right? And so now you're like, okay, now what? So you go back to the problem. The problem is saying solve for m and b. Well, okay, that isn't getting me anywhere because I have too many unknowns. You have to get rid of some of your unknowns. One way to do that is by plugging, like substituting. And you can substitute y with mx plus b. Okay?
Is that why they wrote out y is mx plus b? Because I feel like if we didn't have to use it, they wouldn't write it out.
Well, I mean, it could have been any other function, right? Like they just tell you, they're just giving you a function and asking you if it's the same, right? Okay, so this is what we have. And so now I have to solve for m and b. How do you solve any equation? You set it equal to 0, right? Well, let's just do that. So 0 equals 2x minus mx minus b minus m. Here's the tricky part. How to solve this? All this has to equal 0, right? Okay.
I have an idea.
Yep, tell me.
Would you substitute the m for 2x minus y?
No, because then you just get y, but you just get what we started with 3 steps ago.
Oh.
Let's factor this.
Oh.
Let's just factor this. Let's do 2 minus m x, yeah, minus b plus m.
Oh.
Why have I done this? I've put it into the same form, into a linear form, right? Look, this looks like mx plus b, doesn't it?
Whoa.
Yeah? Okay. If this is equal to 0, that means this, how does all that equal to 0? That means whatever that is should have equaled 0, and whatever this is should equal 0 independently.
Oh, wait.
So back in the day in pre-calc honors, when we're solving differential equations, there is one part, no, we didn't do that. When we do decomposition of, partial fractions, you remember partial fractions? What did we do there? We had something like, you have 3x cubed plus 5x squared is equal to a plus b x cubed plus c x squared. Do you remember that? And then what we did is we said, okay, the x cubed term and the x cubed term, right? Let's match the coefficients. A plus b equals 3. Right?
I do remember that.
I don't remember by name, but it's simple.
Right. So the point being, if you want all of that to be equal to 0, how do you equal that to 0? Well, the only way to do it is if you had 0x minus 0. Okay, that's where all this would equal to 0. So you say 2 minus m is equal to 0. And then b plus m is equal to 0. That means m is equal to 2. And if b plus 2 is equal to 0, b is equal to negative 2. And there you have it.
That's so cool.
Yep. Yep. It is a wow.